Okay, I see most of you have filled out the attendance form. And there are three students haven't filled up. Okay, please fill up the form as soon as possible. Okay, before I start the class, I have one announcement about the submissions of assignment. Okay, the deadline of the submissions of your assignment report, okay, is tomorrow. Okay, tomorrow is 31st of March. Okay, it's Thursday. Okay, it is Thursday. Okay, but due to request from your course mate, okay, uh, whether can extend the deadline or not. Okay, I have make the decisions to extend the deadline. So for all of you to know, the deadline of the submissions of assignment report, okay, will extend until Sunday. Okay, Sunday is 3rd of April. Okay, uh, so make sure you can complete the assignment report and submit by this Sunday. Okay, for some of you who have finished the report, okay, you can submit early. Okay, I have just assigned the submission today, okay, just now. Okay, you can submit your report if you have finished. Okay, for those still need time to finish, the deadline is Sunday. You must submit before Sunday. Okay, this Sunday. No more extension. Okay, the extensions that I can give until Sunday only. Okay, today's we have 2 hours lecture class. Okay, I will use a 1 hour or maybe less than 1 hour of this lecture hour, okay, to discuss the tutorial. Okay, the tutorial for some of the questions I haven't finished. Okay, I want to discuss and do the revisions with you. Okay, because the questions in tutorial 4, okay, some of the questions are quite important. Okay, I didn't ask you to try during the tutorial class. Okay, but in this uh, lecture class, I want you to revise back. Okay, and also at the same time, I discuss the answer with you. Okay, for some of the questions. Okay, after the tutorial discussion, okay, then I will continue with my lecture, okay, on wire modeling. All right. Okay, so now I will start our class. Okay, I think most of you are quite busy. I'm not sure whether you have time to do all the questions in tutorial 4. Okay, so today the question that I want to discuss with you is on dynamic logic circuit. Okay, this topic is also quite important. Okay, you will have to study. Okay, you have to study what has been covered in this topic. Okay, so this is the questions given in tutorial 4. Okay, they are 4 questions here. Okay, okay, let's have a look on these questions. Okay, question 12. Um, Determine and explain the functionalities of the circuit as demonstrated in figure 3. Okay, so this is figure 3. Okay, okay. Can you try and find out what is this circuit for? I give you time. Okay, I give you time to find the answer. Okay, you can refer to the lecture notes. Okay, I want you to go and find out because uh, it can help you to revise back. Okay, uh, what is it about? Okay, what is this a circuit for? And then you need to revise and understand. Okay, I will wait here for the answer. If you get the answer, you can post it in the chat box. Okay, I will give about 5 minutes. Okay, to find out. Okay, if you need more time, please let me know. Okay, if you already have the answer, you can give me. Okay. Okay, anyone is trying the questions? Yes. Okay. Are you able to find the answer? Yes. Okay, Jie, what is the answer? Okay, correct. Okay, it is a voltage bootstrapping. Okay, what is the circuit used for? Oh, okay. Correct. The drop of the threshold voltage is at which point? Vx uh Vx the drop of threshold voltage. Vx is the threshold voltage, right? M2 and M2 transistor. The drop of the threshold voltage overcome the drop of the threshold voltage, and then the drop is at which point? You mean that just now you say is M2 transistor output, or at which point output? This point? This point? Okay, let me double check again. Okay, the V not max here. Okay, I want to double check on the V not here. Is it an output? Okay, if it is an output, means that there is a threshold voltage drop. at the output. Okay. Um, okay. The informations that I have provided to you in this note is not quite complete. Okay. On the explanation. Okay. The one that I show you here is correct, but then the explanations on the function and then the circuit is not complete. Okay. I have one reference here, which I think I can directly show you so that you can read yourself as well. Okay. Yeah. If I share here, all of you cannot see from the projector. Okay, I want to share here. Let me see what can I do. Okay, I think maybe I upload to the drive. CMOS digital integrated circuit. Okay. Okay, give me a few minutes. Okay, I am trying to show you the reference book that I refer. Okay, for the explanations of this circuit. How come hang already? Okay, my computer hang. What happened? Okay, students, I'm having a issue with one of my computer. Okay. Okay, I need to solve the issue now. Okay, at the same time, okay, I want you to refer to this one. Okay, you can read. Okay, you can read yourself this one. Okay, this is the explanations for the circuit. Okay, for this circuit is the original circuit that is with the drop of the threshold voltage. Okay, um, the one that I asked you to find out what is the functions is this circuit. Okay, this circuit is used to overcome the drop of the threshold voltage. Okay, I should share you the reference book, this reference book, then you can read. Okay, now I can only show you one page. Okay, let me see what can I do. Uh, okay, I have just upload the reference book in Google Classroom. Okay, you can download and have a look. Okay, I will solve my computer issue now, and then you please you take this uh, the time, okay, to read. Okay, you can refer to this one. Okay, this circuit you can find in the page 372, 372, and 373. Okay, okay, I will write here. Maybe you can directly refer to the page here. Okay, and you can read yourself. Okay, I don't want to explain more because sometimes I think when I explain more, you also cannot get. Better you read yourself. Okay, sorry. I just find out that I didn't open my mic. Okay, I repeat what I said just now. Okay, I show you, just now I show you the reference book. Okay, if you have a read on this reference book, okay, okay, you will understand, okay, what is the functions of this circuit. Okay, just now G already give the answer. Okay, this circuit is called as a voltage bootstrapping circuit. Okay, it is used to reduce it is used to overcome, okay, it is used to overcome the drop of the threshold voltage. Okay, this circuit is to replace this circuit. Okay, this circuit, if you see here, okay, it is without the capacitor at the output. Okay, no capacitor. Okay, and the output here at the output node, okay, there will be a drop by the threshold voltage. Okay, so to overcome this, okay, additional capacitance and a transistor are added in this circuit. Okay, so you see here, the difference is at the output. Okay, this part. Okay, there is a two capacitance, CS and C boot, and M3. M3 is the transistor. Okay, so with these two capacitance and the transistor, it can use to overcome the drop of the threshold voltage at the output. Okay, just now, uh, okay, just now I show you the lecture notes. Okay, in lecture notes, okay, the explanations in the lecture note is not quite complete. Okay, it's not quite complete on the circuit. Okay, so you have to refer to the reference book here. Okay, you need to refer back to the reference book to understand the complete functions of this circuit. Okay, okay, so in my notes here, okay, this we note max. Okay, this we note max is actually indicate the voltage at the output node. Okay. Okay, so when you do the revision, please make sure that you are not only referring to these lecture notes, okay, you also need to refer to the reference book, okay, to read the explanation. Okay, this can help you to understand better. Okay. Okay, just now I talk about this circuit. Okay. One more I want to add. Okay. In order to overcome the drop of the threshold at the output node, okay, there is a conditions that must fulfill. Okay. Okay. This circuit you see here, there is a CS and C boot, right? Okay, and with a transistor. Okay. This capacitance value for C boot and CS, they must be equals or sorry, okay, the C boot, okay, C boot, the capacitance is equals or larger than CS, okay, and then in order to overcome the drop of the threshold voltage, okay, at the output, okay, the C boot, the capacitance of C boot must be larger than the CS. This is the condition that must be fulfilled so that the V out will be equals to VDD. Means that this is when the M2 is on. Okay, when here is on, okay, V out is VDD. And if C boot is larger than CS, then there is no drop of the threshold voltage. Okay, for this circuit. Okay, if the C boot is less than CS or there is no C boot or CS, then the V out will be reduced by a threshold voltage. Okay, so this is the point that I want you to know. Okay, you must understand this. Okay, so now I go to the next question. Okay, I already showed the answer for question 12. Okay, make sure you do the revisions again later if you still cannot understand. Okay, now I goes to question 13. Okay, question 13, part A. Given a combinational CMOS logic circuit in figure 4, redraw and show the circuit in domino logic circuit. Okay, there are two circuit given here, logic circuit. This is part 1 and part 2. Okay, both of this circuit is a CMOS circuit. Okay, this is a CMOS logic circuit. This is CMOS logic circuit. Okay, and this CMOS logic circuit, we can represent it to a domino logic circuit. Okay, what is domino logic circuit? And then how to draw it in domino circuit. Okay, again, you have to refer back to the lecture notes. Okay, the lecture notes, there's examples there. Okay, to show you what is it about domino logic circuit. Okay, now I goes to the lecture notes. Okay, so this is a domino logic circuit. Okay, we call it domino CMOS logic. Okay, or domino CMOS logic circuit. Okay, it's a similar. Just that there is a domino in front of the CMOS logic circuit. Okay, for domino CMOS logic, okay, this is the figure. Okay, this figure is a domino CMOS logic circuit. Okay, you see the difference here. Okay, there is a VDD as usual and the ground. Okay, and then there is a PMOS and also a NMOS. Okay, in domino, PMOS and NMOS must be present. Okay, must be drawn in this circuit. Okay, and the input, okay, both of the input must be connected to the clock. Okay, means that this circuit is operated based on the input clock. Okay, it's not based on the voltage level. Okay, not input voltage, not input voltage level, but the clock. Okay, and here the middle one, this middle is the NMOS logic. Okay, or we call it as pull down network. Okay, just now you see that there are two CMOS logic given. Okay, so the two CMOS logic circuit, they can be drawn in this way. Okay, when you can draw it, okay, when you draw in this way, so that circuit you call as domino CMOS logic circuit. Okay, so in the circuit given, there is in the circuit given in the question 13 in tutorial 4, they are pull up and pull down network. Okay, so to draw in domino CMOS logic, okay, only NMOS is applicable. Okay, you can take the NMOS logic, means the pull down network, and draw it here, okay, to form a domino CMOS logic. Okay, can you get me here? Okay, so the circuit, this circuit, okay, this circuit you see here, this is a CMOS circuit, okay, with pull up network and pull down network. Okay, this is output. Okay, if we want to draw a domino logic circuit, okay, so the circuit should be like this. There is a VDD and also a PMOS. Okay, and here is the pull down network. This is pull down network. Okay, means only this part, okay, can use to redraw in domino logic circuit, means here. Okay, and then there is a NMOS transistor. Okay, and this is the input. This is the clock. Okay, so this is called as domino logic circuit. Okay, for part 2, okay, for this circuit, also the same. Okay, it's also the same. It is a similar, okay, it is also a domino logic circuit. Okay, just that what you need to modify is the pull down network. Okay. Okay, so I will leave the part 2 for you to solve, okay, and draw. Okay. So I assume that no question from you now. Okay, now I goes to part B. Okay, this question is not difficult. Okay, if you understand and you try the questions, okay, it's actually it is quite easy. Okay, it is actually quite easy. Okay, now I goes to part B. Compare the schematic circuit drawn in question 13A with the original circuit. Deduce the importance of domino logic circuit. Okay. After you draw the domino logic circuit, okay, this is the schematic of the domino logic circuit, and this is also the schematic. Okay, and this schematic is the schematic of CMOS logic circuit. When you compare these two, what can you find out? What can you conclude here? Okay, what can we conclude here? Okay, these two circuit, okay, these two circuit, this and this circuit, when you compare, what can you see? Okay, I give you a clue. What about the complexity of the circuit? Okay. Okay, in terms of complexity of the circuit, What is the difference here between these two schematic? And also if in terms of the number of transistor, what is the difference of these two circuits? Okay, maybe I ask like this. Okay, this schematic of schematic of CMOS logic. How many transistor? Nine? Ah, number of transistor is 10. Then how about this domino logic circuit? Okay, 7. Ah, okay, correct. Number of transistor is 7. Okay, so from the number of transistor here, okay, we can say that the use of the number of transistor is reduced in domino logic circuit. Okay, and then if you compare the complexity of the logic circuit between these two, you can see that domino logic has a more should I say simplified? Okay, the complexity is less complex. Okay, the circuit is less complex. Okay, so if we have a very complex CMOS logic circuit, okay, we can not only draw in this form of a schematic, but we can also draw in another form of circuit, which is in a domino logic circuit. Okay, okay, if they are drawn in domino logic circuit, then the complexity of the circuit can be reduced, okay, with reductions of the numbers of transistor. Okay, so this is for the answer of part B. Okay, okay, so now I goes to question 14. Okay, before I go to question 14, I just see Tiongde questions. Okay, do we need to include the buffer? This is for which questions? Is it the question 12 that you are asking? Question 13. Okay, just now you mentioned about the buffer. Okay. Okay. There is a buffer here. You mean this buffer? Okay. Yes, you need to include. Okay. This is the generalized circuit diagram of a domino CMOS logic circuit. You need to include as well. It is at the output of the domino circuit. Mm.
The original schematic for the CMOS didn't have the buffer, we also need to add ourselves.
Yes. Okay, so my answer is yes, you need to include the buffer. Okay, now I goes to question 14. Explain the operations of the domino logic circuit. Okay, this one I don't think I need to discuss the answer with you because you can find out yourself. Okay, since I already give you the reference book and also some of the operation is also explained in the lecture notes. Okay, so I think you can read yourself and also understand yourself. Okay, the operation is not difficult to understand. Okay, it's based on the high and low clock. Okay, and then the high state or low state of the clock can determine one of the switch or one of the transistor state. Okay, the state of the transistor will determine the output. Okay, so I will leave it to you to solve. Okay. Okay, for 14, I think no problem. Okay, now I goes to question 15. Okay, question 15. What is NORA CMOS logic circuit? Briefly discuss its advantages over the domino logic circuit. Okay, this is another uh, type of CMOS logic circuit. We call it as NORA. Okay, so you need to show and then describe what is NORA CMOS logic circuit. Okay, for these questions, the answer also can refer to the lecture notes. Okay, in lecture notes, I didn't include all the informations about NORA. Okay, you can actually find more informations from the reference book. Okay, so this is the circuit diagram of a NORA CMOS logic. They are quite this is a circuit, okay? It is quite similar to domino CMOS logic circuit. Okay, both are quite similar. Okay, in NORA CMOS logic, okay, you see here, okay, the difference is the output. Okay, I see maybe I use another example. This is okay. I use these examples. Okay, I prefer to use this. Okay, this is a NORA circuit. Okay, NORA circuit, similar with domino CMOS logic. Okay, with PMOS and MOS, and they are connected to the input clock. Okay, and also there is a NMOS logic block. Okay, this NMOS logic block means the pull down network. Okay, and then here is the output. Okay, the output here is connected to an inverter. Okay, this is the buffer inverter. Okay, and this buffer inverter is connected to another NMOS stage. And then the difference here is at the output here, okay, it is connected to the PMOS. Okay, this is PMOS logic. Okay. NORA CMOS logic has different stages. Okay, the circuit has alternating NMOS and PMOS stages. Okay, alternating PMOS and NMOS stages here means that in the circuit here, okay, there is NMOS logic block and also there is a PMOS logic block. Okay, and here the PMOS logic block, one of the input is connected to the output of this domino logic circuit. Okay, and then here in this second domino logic circuit, this is not second domino logic. Okay, I cannot say this because this is a PMOS logic. Okay, this circuit, the second circuit here, okay, the input, you see the clock here is inverted clock. Okay, this is inverted clock, means they are operated, these two transistor are operated operated opposite than this circuit. Okay, so you must remember this. Okay, the difference between the second stage and the first stage, okay, is the second stage of the circuit here, okay, is consists of PMOS logic circuit and with the inverter clock. Okay, and then the third stage here, okay, is the NMOS logic block. Okay, and also one of the input is connected to the output of the second stage. Okay, so at the output, all the output here are connected to the buffer inverter. Okay, so the whole circuit, we call it as NORA CMOS logic. All right. Okay, so what is the advantage? Okay, the question just now, okay, ask what is the advantage of this NORA CMOS logic? Okay, the advantage already stated here in the lecture notes. Okay, static CMOS inverter is not required at the output of every dynamic logic stage. Okay, and direct coupling of logic block is feasible by alternating NMOS and PMOS logic blocks. Okay, and it is compatible with domino CMOS logic. Output of the NORA NMOS logic blocks can be inverted, okay, and then applied to the input of a domino CMOS block, which is also driven by the clock signal. Okay, it allows white line system architecture. Okay, so these are the advantages. Okay, so this is all the discussions for tutorial 4. Okay, for dynamic logic circuit under tutorial 4. Okay, I think I don't need to upload any solutions for tutorial 4. Is it? Which question?
Question 13.
13. Okay, what is the question?
If let's say we convert the CMOS logic circuit from here to the domino logic circuit,
Mm.
then we need to add the buffer logic. That means the transistor will be more than the original circuit for the second part.
Oh, okay, yeah. 1, 2, 3, 4, 5. 5 plus 2, 7. Now is 7. If plus the buffer inverter, there is another 2 transistor, right? But 2, 7 plus 2 mean 9.
The second one.
This one, right?
Yeah.
This one got 3 transistor.
So before convert, it's 3 plus 3, so it's 6.
Oh,
Then after convert, 3 plus 2 up and down, another 2 buffer. So it's 3 plus 2 plus 2 is
okay, I get you. Okay, okay, I get what you mean. Okay, if we exclude these two, and then we only consider the number of transistors in pull-down network, then we can mention that the number of transistors is reduced.
So the transistor is only referring to the
inside the NMOS logic block. Mm.
Also, with answering the questions like B1, we need to specify only for the animals, right?
Yeah. Mm. Okay. Okay, so for this tutorial 4, I'm not going to give you the solution, all right? Because I have already discussed some of the solution with you, and others that I haven't discussed, I expect that you are able to find out the solution. Okay, I hope should be okay, right? Mm. Okay, so we take a break, about 10 minutes break. Then I will continue with lecture.
like that. Very soon. Okay.
Okay, I will continue the class now. Okay, I will try to finish chapter 8 today. Okay, not many slides. Okay, today I will cover about wire modeling with delay. Okay. Okay, this wire modeling with delay are related to the RC. Okay, RC, the resistance and the capacitance. Okay, that also the parasitic. Okay, resistance and capacitance, as mentioned before, both are parasitics. Okay, so previously I have a cover about what is parasitic capacitance. Okay, so today's also it will be mentioned. Okay, for the modeling of these wire models. Okay, um, the wire. Okay, wire we also call as interconnect. Okay, wire itself can induce capacitive coupling. Okay, when there is a signals transmit. Okay, and then the wire, there is a parasitic capacitance. Okay, and this parasitic capacitance we can actually estimate. Okay, based on the modeling. Okay, so here is about the estimations of the interconnect parasitic. Okay, the transmissions line effect have not been a serious concern in CMOS VLSI chip since the gate delay due to capacitive load components dominated the line delay in most cases. Okay, so this statement means that transmissions line effect is not a serious issue. Okay, in CMOS VLSI chip. Okay, why is not a serious issue? Because the gate delay, gate delay dominated the line delay. Okay, means that in a CMOS circuit or in a CMOS chip, okay, the delay is caused by the gate and also caused by the line. Okay, the line here means the wire, okay, the transmission line. Okay, this is means by the transmissions line. Okay, delay can cause by many can cause from many component. Okay, can it caused by the gate, okay, caused by the gate or caused by the line. Okay, and which one dominated? Okay, it depends on the size of the chip. Okay, different technology used, then the delay, the gate and line delay also will be different. Okay, so for this one, okay, when the gate delay dominated the line delay, then the transmissions line effect will not be a serious concern. Okay, however, as the fabrications technology move to finer submicron design rules, okay, means that um, a smaller feature size of the transistor in submicron, okay, are fabricated. Okay, then the intrinsic gate delay tend to decrease significantly. Okay, and the transmissions line effect and signal coupling between neighboring line become more pronounced as the width of the metal line streak. Okay, by contrast, the overall chip size and the worst case line length on a chip tends to increase, mainly due to increasing chip complexity. Thus, the importance of interconnect delay increases in submicron technology. Okay, it is illustrated in figure 6.13, where typical intrinsic gate delay and interconnect delay are plotted qualitatively. Okay, this is a figure 6.3. Okay, this figure plot the delay of the gate and also the interconnect, okay, versus the feature size of the transistor in the chip. Okay, the feature size list here is a sub-micron technology. Okay, this is sub-micron technology. So as you see here, as the feature size of the transistor decrease, okay, if going to the right, this is decrease. Okay, the feature size decrease. Okay, from 2 micron meter to 0.35 micron meter means the feature size is minimized. Okay, and when the feature size of the transistor is minimized, then you can see that the delay also will vary. Okay, delay will vary. Okay, the delay here are for this gate delay and interconnect delay. Okay, there are two lines. Okay, so this is for the gate delay and this is for the interconnect delay. Okay, when the feature size of the transistor is at 2 micrometer, okay, the gate delay is higher than the interconnect delay. Okay, so this means that gate delay dominated the line delay. Okay, and when the feature size of the transistor is smaller, okay, at this point 0.35, okay, if we compare these two delay, okay, you will see that interconnect delay will dominate the gate delay. Okay, this is how we should understand the graph. Okay, in order to deal with the implications and to optimize a system for speed, okay, chip designer must have a reliable and efficient means for estimating the interconnect parasitic in a large chip and stimulating the transient effect. Okay, when we talk about speed, okay, it is related to delay. Okay, if a chip induce large delay, it will also affect the speed, okay, the speed of the system. Okay, so a chip designer, they must estimate, okay, the interconnect parasitic. Okay, why have to estimate the interconnect parasitic? Because this interconnect parasitic contribute okay, this interconnect parasitic contribute to line delay. Or you also can call it as interconnect delay. Okay, how to do the estimation? Okay, it is based on the RC wire delay model. Okay. Okay, and using these RC delay models, the transient effect can be investigated. Okay, this will be mentioned later. Okay, in a large-scale integrated circuit, the parasitic interconnect capacitance are among the most difficult parameters to estimate accurately. Figure 6.15 shows a simplified views of 6 interconnections. Each interconnect line is typically surrounded by a number of other lines, either on the same level or on different level. Okay, so you see here, this is the interconnect, okay, interconnect layers or interconnect line. Okay, they are at different level, okay, and all of these interconnect lines, they have a parasitic effect, okay. Okay, now wire model. Okay, wire model can use to models the interconnect parasitic. Okay, interconnect parasitic include the capacitance, resistance, and inductance. Okay, this interconnect parasitic is actually an unwanted effect. Okay, it is unwanted effect. Okay, why? Because it will reduce the reliability, okay, of the chip, and also affect the performance and the power consumptions. Okay, the figure show here, okay, the wire model, okay, with capacitor, resistance, and inductance. Okay, this is the modeling. Okay, and also the wire models can also include with only one capacitance. Okay, so this is the models, wire models with only the capacitance. Okay, so there are certain conditions where we can exclude the inductance effect and also the resistance. Okay, and leave only the capacitance. Okay, in the next few slides, okay, it will be mentioned what are the conditions. Okay, parasitic simplifications. Inductive effect can be ignored if the resistance of the wire is substantial enough, as is the case for long aluminum wire with small cross section. If the rise and fall times of the applied signals are slow enough. When the wire is short or the cross section is large or the interconnect material has low resistivity, a capacitance only models can be used. Okay, so this is the conditions. For a wire models that has only capacitance, then it means that the wire is a short. Okay, wire is a short, and okay, this wire is a short, and the cross sections area of the wire is large, and the interconnect material has low resistivity. Okay. When the separations between the neighboring wire is large, or when the wire run together for only a short distance, inter-wire capacitance can be ignored. And all the parasitic capacitance can be modeled as capacitance to ground. Okay, so this one is for the case when the separations between the neighboring wire is large. The inter-wire capacitance can be ignored. Okay, you learn about what is inter-wire capacitance, right? Okay, so inter-wire capacitance, it can be ignored when the separations or the spacing between the neighboring wire is large. Okay, and also when the wire run together for a very short distance. Okay, the signal propagations delay due to large interconnect capacitance is a major factor which limits the performance of CMOS digital's integrated circuit. The system speed is ultimately restricted by the current driving capability of CMOS gate that drive large capacitive load such as the words line in memory array or data bus line between large logic blocks. The problem of driving large off-chip as well as on-chip load is traditionally solved by using specific CMOS buffer circuit with enhanced circuit driving capability. Okay, so on the slide with the statements here, emphasize the current driving capability of the gate is actually quite important. Okay. Okay, wire delay models. Okay, there are different models. Okay, to represent the wire delay. Okay, and the ideal one we call it as ideal wire model. Okay, what is ideal wire models? Okay, it is a models for ideal wire. Okay, and then these models shows that the same voltage is present at every segments of the wire at every point in time at equal potential. Okay, only holds for a very short wire. Okay, and for example, the interconnects between very nearest nearby gates. Okay, okay, so for ideal wire, it is only for the ideal case and also only for a very short wire. Okay, with all the voltage at the same level. Okay, at every segment of the wire. Okay, and then there is another wire models. We call it as a lump C model. Okay, these models means that it is only with capacitance. Okay, and then the capacitance are all lumped together as one. Okay, you see here the diagram given. Okay, this is a driver with 3 capacitance at the output. All these capacitance can be wire capacitance or output capacitance or okay, output capacitance. There are several capacitance that sum up to become output capacitance. Okay, so this capacitance here we can lump together, okay, and we draw it in this way, okay, with only one capacitance. We call this capacitance as lump capacitance. Okay, so the descriptions here given is when only a single parasitic component CRL is dominant, the different fractions are lumped into a single circuit element. Okay, this when only a single parasitic component. Okay, so lump C models means that a single parasitic components of C. Okay, if it is a lump C, means the parasitic components will be the C. Okay, is the dominant one. Okay, and then for these models, okay, the resistive component is small. Okay, and the switching frequency is low to medium. Then only we consider the lump C model. Okay, the wire itself does not introduce any delay. The only impact on performance come from the wire capacitance. Okay, there is another models called LAM RC models. Okay, this is the total wire resistance is lumped into a single R and total capacitance into a single C. Okay, and this model is good for short wire and pessimistic and inaccurate for long wires. And another models we call it as distributed RC model. Okay, this model is used to show the circuit parasitic that are distributed along the length L of the wire. Okay, and the capacitance and resistance are evaluated per unit length. Okay, so here the figure show you in this circuit, there is a resistance and the capacitance. Okay, and they can use to lump, they can lump together. Okay, they can lump together to simplify. Okay, in this way. Okay, this is the simplified circuit. Okay, the delay is determined using the Elman delay equations. Okay, this is Elman delay equations. Okay, this tau means the delay. Okay, this is delay. This is C, capacitance, and this is resistance. Okay, this shows the multiplications of RC. Okay, and okay, the multiplications of RC of each part. Okay, and then the summations. Okay, they need to multiply and then sum. Okay, sum with another RC. Okay, this is the summations. So this is how we evaluate the delay. Okay, RC equivalence models of the CMOS circuit can be solved by using the Elman delay model. Okay, the equations that show just now, okay, indicate this one. Okay, this is the examples of an the Elman delay. Okay, used based on these equations. Okay, so for this one, this is a delay, RC delay. Okay, or I should say the RC that is based on the delay that is based on the RC. Okay, so this is a circuit with RC. So all these RC can be the resistance and capacitance in the wire. Okay, and if we want to evaluate the delay of the wire, we can use this Elman delay equations. Okay, this is R1 C1 plus R1 plus R2 C2. Okay, and so on. Okay. And for a small resistive components, low to medium frequency range, only capacitance component can be considered. Okay, next shows the equivalence RC circuit models for NMOS and PMOS. Okay, a figure 4.5 is given here. Okay, this is NMOS transistor, and this is PMOS. Okay, so both transistor we can use it to draw an equivalence RC circuit models. Okay, he already show you this is an equivalent RC circuit model. So you see here in the respective transistor, there is a resistor. Okay, there is a resistor, there is a capacitance. Okay, so the capacitance is at the input of the transistor. Okay, input here is means the gate. Okay, this each of the terminals here has a capacitance. okay, because they are connected, okay, to another point, okay. So input, gate, source, and drain terminals are all connected to the capacitance. Okay, and you see here, this is the resistance that is that is in series with the switch. Okay, last time I mentioned about the on resistance. Okay, so it is actually about this one. Okay, so this is a resistance. Okay, and PMOS also, you see, gate, source, and drain. These three terminal has a capacitance, and also there is a resistance in series with the switch. Okay, this whole RC equivalent circuit indicate a transistor. Okay, PMOS or NMOS. Okay, what is mean by K here? Okay, um, K is actually the width. Okay, the width. This is the K. Okay, the width of the transistor will determine the amounts of the capacitance and the resistance of that transistor. Okay, the PMOS transistor has approximately twice the resistance of the NMOS transistor because holes have lower mobility than electrons. Okay, so now discussing about the width of the transistor. Okay, PMOS transistor usually has a width larger than the NMOS, and then it is by a factor of 2. Okay, this is normal. Okay, 2 or 3. Okay, I read before from other articles, not exactly twice. Okay, but can be larger than 2. Okay, 3. Okay, can goes to 3. So the width of a PMOS transistor usually is larger because of the hole, okay, in PMOS have lower mobility. Okay, so the width must be larger in order to have the same amount of the uh, mobility, of the same of the amount of current. Okay, in order uh, to reach, okay, the same mobility as of this NMOS. Okay, so you see here, for these two transistor, NMOS and PMOS, the width are different. Okay, they are indicate with this K. Okay, the width, these two width are different, and we can see through the K here. Okay, okay, at the gate here, this is KC is the same, capacitance is the same, except that here the transistor, the resistance. Okay, this is the resistance. The resistance for PMOS, you see here, PMOS resistance here is twice. Okay, it is twice. R divided by K, but multiply with 2. This is twice. Okay, when the width is double, okay, it has only effect on this, the resistance. Okay, so I have 5 minutes. Okay, I think I cannot finish it today. Okay, maybe I continue one more slide, then we end the class. Okay, this slide shows the RC equivalence of an inverter. Okay, this is an equivalent circuit for a fence out of one inverter. Okay, when we have neglected the wire capacitance. Fence out of one means the inverter is driving one similar inverter gate at the load. Okay, so this is a fence out of one inverter. It means that this driver inverter is driving another load. Okay, this is the load. Okay, this load is a fence out of one inverter. Okay, I state here, this is driver, this is load. So this driver transistor is driving this inverter that is function as the load. Okay. Okay, you see here there is a fence out of 4 inverter. It means that this inverter is driving another 4 inverter. Okay, these 4 inverter are the loads. Okay, so this inverter, the entire circuit, it is called as fence out of 4 inverter. Okay, if we want to represent this inverter with RC, okay, we can redraw it in this way. Okay, this circuit is a RC equivalent circuit. Okay, this RC equivalent circuit is for the fence out one of inverter. Okay, you see that the terminals, source and drain terminals here are all connected with the capacitance. Okay, except the gate of the capacitor is not shown here. Okay, so the we have to determine the output capacitance. Okay, as given here, we can determine the output capacitance. So the capacitance at each of the terminals of the source and drain are given. Okay, are drawn in the diagram here. Okay, and the resistance here also draw with the switch. Okay, for the PMOS and NMOS. Okay, and you see here, okay, the width, okay, of the PMOS and NMOS, okay, is given here, 2 and 1. Okay, this indicate the K. Okay, K is the width. Okay, and then the capacitance here is actually determined by the K. Okay, determined by the K. Okay, the just now the previous slide I remember. Okay, the capacitance is actually not indicate that it is determined using the K. Okay, but here show it is actually multiply with the width. Okay. Okay, so I need to look into that. Okay, maybe the figure there is not accurate. Okay, so okay, if I use this figure, okay, we follow this one first. Okay, for this, the capacitance we have to determine based on the width, okay, of that transistor. Okay, you see here, this is 2C, 2C, and this is 2C. This is actually indicate this part, the PMOS. Okay, the PMOS part. And then here with C only, it is for the NMOS. Okay, this is for NMOS. Okay, to lump them all together, okay, we can redraw this circuit in this way. Okay, so there will be an resistance and then a capacitance. This capacitance is lumped together. Okay, 6C is based on this 2C plus 2C plus C and C. So it is 6C. This is the output capacitance. Okay, so output capacitance is a 6C. Okay, if you want to determine the output capacitance for a fence out of 4 inverter, okay, so this is how we should determine. Okay, at this inverter, the driver inverter, okay, there is, okay, maybe I shouldn't draw here. Okay, I will directly mention here. I think all of you can get. Okay, 2C and C. 2C and C is the output capacitance at drain terminal of be most and most means only this one. Okay. Okay, I see I don't have enough time already. Okay, give me 5 minutes. I will end the class. Okay, I need 5 minutes. Not maybe not five, less than 5 minutes. I will end soon. Okay, so now I'm saying this one, this part. 2C and C is from here. Okay, the driver inverter. Okay, and then this 2C. Okay, I use another color. Okay, this 2C and C, okay, is here. Okay, 2C and C. And then Y is multiplied by 4 because of 4 inverter and the output of the driver inverter. Okay, so the total output capacitance will be 15 capacitance. Okay, so I think this is clear. Okay, so I will end here. Okay, there are a few more slides. Never mind, I will continue next Monday. Okay, so I think there is no further question from you. Okay, about your attendance, I have updated all of your attendance in intranet. Okay, you can check. Okay, so I think we can dismiss class now. Okay, thank you. I will see you again next Monday.